All right, so this is a special case. We're comparing means, so it's kind of a little like 10.2, but it's really not, okay? This is a really kind of isolated special case in comparing means, okay? It's called paired data, and paired data has an absolute, it has a own little thing to itself, okay? So if you go to page 673, the top, there's a paragraph that starts at section that says, start with section 10.2. Kayla, would you go ahead and read that for us?
Section 10.2 showed you how to perform inference about the difference between two means when data come from two independent random samples or two groups in a randomized experiment. What if we want to compare means in a setting that involves measuring a quantitative variable twice for the same individual or for two individuals who are much alike? For instance, a researcher studied a random sample of identical twins who had been separated and adopted at birth. In each case, one twin, twin A, was adopted by a high-income family and the other, twin B, by a low-income family. Both twins were given an IQ test as adults. Here are their scores.
All right, thanks. Okay, so this is kind of, let's look at this experiment itself first. Okay, the experiment itself is, what are we doing here? What is this basically called? There's a thing that we call this. What are we calling this? What is this called? It's kind of like a nature versus nurture type of thing, right? Because you are separating identical twins at birth and you're giving one to a high income family and one to a low income family. You're to see if the IQs come out to be the same, right? If you believe in nature, they should be the same. If you believe in nurture, it'll be different, right? Because you're getting different kind of nurturing there, right? Okay. So if you look at that, we have look at the data. We have twin A, which went to the high income family. You have twin B that went to the low income family. And they have their two different IQs there, right? So what we're really interested in here is that we're not interested in what the mean of the high IQ is or what the mean of the low IQ is. We're looking for the difference here, right? We're looking for the difference between the same identical twin, right? So identical twin meaning what? They're basically the same person, correct? When you were born, they're basically the same person if they're identical twins, right? So let's get a definition here. The definition of the green box. The green box says, paired data result from recording two values of the same quantitative variable for each individual or for each pair of similar individuals, right? Okay. So this is what paired data is. So it's a very kind of isolated, just a really small part of statistics, okay? So let's go to analyzing paired data. So flip the page, if you go there, the very first thing that they did on the top there is, if you notice, again, we're interested in difference here though. So the first thing they went ahead and looked at was the difference, right? And we're gonna go, we found the difference between A and B with A minus B. So the high income minus the low income, right? And if you look at that data, there are 12 sets, right? And they are 8, 5, 9, 6, 5, 8, 1, 6, -1, 10, 1, and 12. So what would you think that there was going to be here? If you were to guess, what would you say? What would your guess be here, Kyle? If you just looked at the data. Anything you can say about the data?
Well, it looks like twin A is smarter.
Twin A is definitely looks like it's smarter, right? Because they're all positive, except
Yeah.
for one, right? Except for one case, right?
Yeah.
And even that case is there, it's like 103 versus 104. They're virtually the same, right? So you could, we're going to guess that, yes, the high income twin, the twin that went to the high income family looks like they will have a higher IQ. Okay, so we're going to take that data, right, and we ran it, and we found that the mean of the differences was 5.833 with a standard deviation of 3.93. Okay, so let's look at the green box underneath there. It says to analyze paired data, start by computing the difference for each pair. Then make a graph of the differences. Use the mean difference, X bar diff, and the standard deviation as your summary statistics. So you're going to go ahead. We're going to go ahead and calculate the confidence intervals and the significance tests using these two things. We're going to use this guy, and we're going to use this guy here, right? The standard deviation of the difference, right? Is that how they wrote that? Let me go and make sure that, yeah, okay. So you have the difference, you have the mean of the difference, and you're going to have the standard deviation of the difference. And you're going to use these two parameters to calculate the significance testing or calculate a confidence interval. Okay? So, like the green box says, the very first thing you do when you notice that it's paired data is you're going to look at the difference, calculate the difference, and deal with those numbers. Okay. So let's look at the example there. There's a math and music example. Let's have Mackenzie read that for us.
Does music help or hinder performance in math? Student researchers Abigail, Carolyn, and Leah designed an experiment using 30 student volunteers to find out. Each subject completed a 50-question single-digit arithmetic test with and without music playing. For each subject, the order of the music and no music treatments was randomly assigned, and the time to complete the test in seconds was recorded for each treatment. Here are the data along with the difference in time for each subject.
All right, thank you. So if you see there, if you look there, you got student 1 through 30, and then you timed it with music and without music, and then you calculated the difference, okay? So let's kind of briefly look at the data that we have, right? So we got 13, 13, 6, 8, 5, and so on and so forth, okay? And actually on A, they did a dot plot. If you look at the solution, it shows a dot plot there, okay? And also in number 3 or C, it says, calculate the mean difference and the standard deviation. When you do that, and you obviously they just went ahead and put in the L1 and did a 1-bar stat, you get the X bar of diff being 2.8. Okay, so the X bar diff was 2.8 with a standard deviation of 7.49. Okay. So based on this, what can you say? We can say that the students scored better, right? The better without the music, right? Because when you took the test with the music, it took you longer to complete it, right? So they would get better without the music. Okay. Now the question is this. Now the real question is okay, is that by happenstance, did you get lucky, or is this just kind of luck of the draw? Or is this actually something meaningful, right? And you would do this by, right, doing a significance testing or constructing a confidence interval, right? So that's what we're trying to find. Okay, we skipped B there. So what did B say? B says, describe what the graph reveals about whether music helps or hinders. Okay, this is what we just talked about, right? There is some evidence that music hinders performance on the math test. 17 of the 30 subjects took longer to complete the test when listening to music. Okay, so that's what we just talked about, right? And again, the question is this just happenstance, or, you know, is there something really going on here? Okay, so let's go ahead and flip the page and we'll talk about constructing a confidence interval here, okay? So again, since it's a confidence interval, right, we're gonna do it just as though we would do the, remember we did the mean difference, right? When you difference in means, what do you find? We did mu1. Yeah. How do we construct the confidence interval for means? What was it? Claire. 10.2 told us what? What do we find in 10.2?
Do you want me to do the conditions or like?
No, just give me the formula.
Oh.
mu1 minus mu2, right?
Mm-hmm.
Plus or minus
Like the T score.
Z star. Is it Z star or T star?
That was T star.
It's T star. Okay, and then what?
Oh, and then we do the. Is it? It's mu. No. Damn. Yeah, over n, and then plus over n2.
Correct. This is what we did, right?
Mm-hmm.
This is what we did. Okay. So we're kind of gonna do the same thing here. Okay. So on this one, what we're gonna do is that we are going to say that instead of using this, we're just gonna use. So what do we find? We found this guy, and we have this guy. We have the mean of the difference, and you have the standard deviation. So instead of this, we're gonna put this, which makes sense. Now, obviously, we don't have N1 and N2. We're going to go ahead and use this guy. Okay? Now, we don't, so since we don't have a different N1 and N2, we don't have to worry about which degree of freedom we're going to use for T, right? Okay? So we're going to be okay with that. So if you go to page 677, this is right there, right? You're going to use this. And then if you go to page 676, you can see the conditions. So go ahead and read the green box, the conditions there. And they're actually pretty much the same as we did with the difference in the means, except for since we don't have a difference in N1 and N2, we don't have to worry about that. Okay, we don't have to worry about only one large counts there, right? If the population itself is normal, doesn't matter what the N is, it's going to be normal, so we're going to be okay. Okay. If the population, if the sample size is greater than 30, then we're good to go also, because the central limit theorem tells us that it's going to end up being normal anyway. So we're good to go there. But if we don't know that it came from a normal distribution and we have N is less than 30, then we just draw a dot plot and look for skewness or outsiders, right? Outliers, right? Okay. Basically the same thing we've done before. Okay. So let's go ahead and go to page 677 and see if we can work one of these out. Okay. So in 677, this is the which one is smarter one. Okay, we're gonna use the same data that we had before, and it says what? To do a 95% confidence interval, So do a 95 confidence interval. So if I do that, the X diff I think was 2.83 and this was 7.9 something. What was it? Oh, here it is. 5.833. So this is 5.83. And we had 3.93 over here. So this was 3.93. So what would we have? We're going to have 5.83 plus or minus. This guy was 3.93. And how many data sets do we have? What was N? How many twins?
12.
12 twins. We have 12 twins. So all we need to do is find the T star, correct? Find a T star. To find a T star, we go back to our book in the back of our tables, right? And it's T-3, T distribution. I look at 11, degree of freedom is 11, right? Because we have n is equal to 12. So I go there and I'm looking for, what was my confidence interval? Confidence interval was 95%. 95%. So if we use 95%, what do I find? I find that $2.201. Is that what we get? Yep, 2.21. Everybody see where I got 2.201 there? Everybody see where the 2.201 came from? So it's that yellow, top yellow one on 11 there at 0.05. Okay, so that's going to be 2.201. So I'm going to put 2.201 there. And if I do this, I am going to get 3.336 to 8.330. So this is our confidence interval. So, Caden, go ahead and conclude for us.
We are 95% confident that the interval from 3.336 to 8.330 captures the true mean difference, high income and low income, in IQ scores among pairs of identical twins raised in separate households.
Okay, great. So what did we miss here? What did we forget to do? We had to do the state, plan, do, conclude. We did the do, we did the conclude, right? But we didn't do this or this, did we? Did we check our conditions? Should we have checked our conditions? We needed to check our conditions, right? So do we know that it's from a normal distribution? Not really sure, right? So let's go ahead and the n is less than 30. So if you go to page 678, you actually had to do the dot plot. If you look at the dot plot, okay, it doesn't look like there are any severe outliers, nor is there any severe skewness. Okay, so we forgot to do that. So we need to do that, right? Everything else we did fine. Okay, everybody understand what we did here? We good? All right, we're gonna stop right here for the first part.